家起，崔家园，陆一凡，姚如歌，李宗浩，Rizky， Jenna， no， 丁，楚南，蔡家峰。Lexi. Okay. For last week, we just wanted to introduce the dielectrical properties of some materials or topics on the Earth. So we classified the materials on the Earth to be 3 groups. The first group is homogeneous. Such as the pure water or some other pure or and isotopic materials. The second is the electrolytic solutions, just like the salt or the sugar dissolved completely in water. The third is a mixed or the homogeneous, the heterogeneous mixture. So these 3 kinds of materials. For the homogeneous material, we can just obtain their dielectric properties by measurements, and this is what we already do, right? So by, for example, by some measurement tools, we can do such things. And the second kind of materials, the electrolytic solutions. Because the one kind of material is dissolved completely in another, so we can also regard them as to be another kind of homogeneous material, and so we can also take measurements on that. So this can always be correct. The third thing is the heterogeneous mixture. So they are composed of several kinds of materials, and something maybe is in the form of the solids or particles or pockets, and their distribution maybe is not always maybe a uniform distribution or maybe ununiform. So certain kind of materials is a little bit difficult to take the measurements on their dielectric properties. And what we usually do is we can take some theoretical models to conduct their predictions of them, and because their properties really depends on the particle sizes, the shapes of the particles, or the inclusions, and their distribution side, and also the volume fraction or volumetric fraction of this kind of inclusions with respect to the host material. All right. So for the for the third kind of material, for the mixtures, we really take 2 kinds of parts of that. One is the host material, all right, and then another one is the inclusions. So for the host material, surely the largest volumetric component we will take. For example, there are some maybe fog in the scale in air. So we can already take air as to be a host material, and the fog particles or small water particles to be the inclusions inside of it. So for solid kind material, as dielectric constant is we use the mixture. Okay, the mixture. Dielectric constant of a kind of mixture, and it can be. It depends on the position of the inclusions and also the orientation of the inclusions with respect to the polarization of our electric field. And so here the inclusions really consider them to be, because it has many kinds of shapes, right? They can be squares or spheres or ellipsoid or the disk. All right. So here we just take it as a general assumption as ellipsoid. So we already take the particles to be in the shape of ellipsoid, and so for example, maybe for the sandstorm and for the calculations, we usually consider them to be small particles and with the shape of ellipsoid. So for the ellipsoid, it has a main orientation, right? So it has finally as the it is composed of two parts. The one part is the average, the mean average unit vector. The mean of the dielectric constant of the mixture, and it equals the average of this part, right? Average of it, and plus another part. So this part is fluctuation part. It's due to the orientation of the ellipsoids. Maybe they have different directions with respect to the polarization of the electric field, and so this would introduce some fluctuations on the total values or the total dielectric properties of the mixture. So, and the average of this part, as we mentioned on Monday, it should be 0, all right? 0, because the distribution of its orientation is random. So the average value of it equals 0. So for our calculations, we already take the mean value of that firstly. So we do the more concentrated on this term. So the mean value of it. So and also we can call it the average relative dielectric constant of a mixture. So the dielectric constant can be separated into two parts, right? The real part minus the imaginary part, and so for this part it equals, in our calculation, equals for the refractive index and the square of it, all right? So that means the refractive index, it can also be a real part and an imaginary part. So the real part equals real part of square root the dielectric constant, and the imaginary part be the dielectric constant of H and minus, all right? It should be minus. So if we have a plane wave propagating in a lossy medium, plane wave propagating in a lossy medium. So its electric field can be expressed as, so for example, it is propagating along the axis, and it can be expressed as 8 node, right, times the propagation constant of the medium, all right, gamma is the propagation constant. So gamma, the propagation constant in a lossy medium. In a lossless medium, we use wave number to represent that. All right. But for the lossy medium, it can be expressed as the the absorption constant and also the phase constant. All right. So absorption and the phase constant. So now, if we want to relate the dielectric properties of the dielectric constant to the absorption and to the imaginary to the phase constant, and we can express that as R equals the keynote absorption related to the imaginary part of the dielectric constant, and it can be expressed as minus keynote and the imaginary part of the square root of the dielectric constant, and the beta equals keynote because it's a phase constant, so it's related to the real part, and can be as this one. All right. So according to this equation, both equations, we can obtain the propagation properties of an plane wave when the transmitting in a lossy medium. And here we need to take care as the lossy medium is uniform and isotropic, right? So from here we can also, if we ignoring the scattering losses inside of it, so the power density is related to all the power of power density. It would be related to the electric field, all right? So here for the power densities, that means it should be the absolute value of the related to the square of the absolute value of the electric field, and so the imaginary part disappears, right? We can only consider just the absorption constant, and it should equals F. Note at zeta equals 0, the initial power density, and when it propagates, it equals minus zeta, right? And it has also a factor kappa, all right? The kappa is called the called the power. It's related to power, right? And also absorption is related to alpha. But it called efficient. So it is called power absorption coefficient, efficient. Sorry, it should be coefficient. Coefficient. And so if when we come back to here to the electric field, because the electric field depends on alpha only, and here becomes kappa A. So that means kappa A equals how much? Alpha. With alpha. It should equal, it related to equal of the electric field, the square of the electric field, right? it equals 2 alpha, alright? So E minus alpha theta squared equals E minus 2 alpha theta equals E minus kappa A theta. So kappa A equals 2 alpha. And also we have, if it is radiated or it focused onto a kind of material from free space, what is it gonna suffer? It's gonna suffer the absorption, and it also led to another parameter that we need to consider is what? You know, do you remember? So, for the I think most of you should remember the skin depth, all right? Also, it's related to the penetration depth. Depth. Delta P equals 1 over kappa A, alright? So this is the penetration depth. And also, the skin depth, it equals skin depth S, delta S. It equals how much? Skin depth means it's related to the electric field, so it equals 2 times the penetration depth. So this is for the propagation of the short review about the propagation of the plane wave in lossy media, and then later we're gonna introduce that to the propagation of the electric field inside of the mixture. And because for the mixture it cannot be a uniform, and so as propagation is gonna suffer the scattering, and also due to the scattering, the multipath component is gonna lead to the interference, and also the absorption inside of it. So this is what we're gonna introduce later. So first now, we're gonna start from the homogeneous material, and as we said, that one of the typical, most typical material for the homogeneous part is the pure water. All right. So for the pure water, and we usually, for measurements or in experiment, we want to take that, and it's very difficult to find pure water, right? The pure water is really very expensive, and the fabrication is very difficult. And what we really take is the distilled water. We just use distilled water to represent the pure water in an experiment. So there is most commonly used theoretical model to calculate or to predict is dielectric constant, and it is usually called a Debye model. For the Debye model, it's related to, it assumes or it considers that it has relaxation frequency for this kind of material. So it has relaxation and because the firstly almost commonly single relaxation, the bimodal. So this is the first one, and so because this model is considers that the water only has one single relaxation frequency, so its dielectric constant can be expressed as the epsilon water equals one term is related to because for any kind of the material, as dielectric constant is frequency dependent. That means in the electromagnetic spectrum, all these frequency components is going to affect. If, for example, we want to calculate the dielectric constant at maybe 1 gigahertz, so we need to consider its spectral lines at all the frequencies over the whole spectrum, like EM spectrum. So the first term is when the frequency increases to infinity, it corresponds to the electric field, and at the dielectric constant plus another term is related to its frequency, its relaxation frequency F is related to it equals half 1 over the 2 pi tau W. The tau W is the relaxation time of this kind of material. So the presence of the relaxation frequency is because, according to the measurement, at the relaxation frequency, the imaginary part of the dielectric constant gonna to be maxima. So of course, so this we can also see that kind of equation is also a semi-empirical equation. It's because it depends, or it was modified according to the measurement. So this is the epsilon W node at frequency equals 0, and also minus related to the infinity. So now for this equation, it considers the spectral lines over the whole frequency spectrum from f equals 0 to f equals infinity, and actually in measurements it's difficult for us to obtain the dielectric properties, especially when frequency equals infinity. So these values are usually obtained by fitting to the mirrored data in the calculations. So as we want to get the real part and the imaginary part, all right? So the real part is obtained by the an image here. So it has real part and also has imaginary part. So the real part equals 7W infinity plus, right? This term minus infinity times divided by 1 plus 2 pi f W square. So this is the real part, and the imaginary part only has 2 pi f W, no minus infinity divided by 1 plus 2 pi f W square. So this is expressions for the real and for the imaginary parts, and so the both parts we can say it depends on the frequency and also depends on the relaxation time or the relaxation frequency. But this for the relaxation frequency, it is usually fixed for one kind of material, so it's only frequency dependent. But it also depends. For example, as we all know that when we wanted to take, for example, for our electronic devices, because for the electronic devices, it also has a operating or the optimum operating temperature, right? Because the semiconductor materials, its dielectric properties is temperature dependent. So for the water, its dielectric property is also temperature dependent. And which term is temperature dependent? Here as the at frequency equals 0, it is temperature dependent. And also the relaxation time is also temperature dependent. So that means the maximum for S, especially for the imaginary part, as maximum is usually temperature dependent. So that means the absorption or the power loss for the EMV propagating and kind of material, it also depends on the temperature of the material. So this is the term. Usually its change would not be that much, but maybe for especially for the high resolution detections or sensing, the small variation or a small change in temperature would also lead to a significant variation in the results. So this is for that part, and for the maximum or for the infinity part, the frequency reaches to infinity part for the water. It usually considers to be constant. Usually is 4.9. Sorry. So if we wanna take a measurement, or we wanna roughly estimate the dielectric constant, the real part of the dielectric constant of a kind of material, the water at high frequencies, for example, to the ultraviolet or X or gamma, it's really, you can just set it to be 4.9. And actually for the, as we already said, for the for the terahertz frequency range or infrared, we also use this value. So this is the this part, and as we said, the relaxation time is also a temperature dependent. So according to the measurements and some guides or some publications, they obtained the expressions for the relaxation time, and it's to the temperature, and 1.119 times 10 to the power minus 10 minus 3.284 times 10 to the power minus 12 temperature, and times 6.938 times or minus 14 t squared minus 5096 times 10 minus 16 squared cube. So here the temperature for the when we want to calculate the dielectric properties of the materials with respect to temperature. So the temperature we usually use it as the Kelvin instead of the degree centigrade. So this part we need to take care. So as we said, the relaxation frequency is related to the relaxation time, all right? So for the relaxation frequency, H can be expressed as F node equals 1 over 2 pi tau W, and this is the relaxation frequency. So for the relaxation frequency, because the relaxation time is temperature dependent. So as measurement, the relaxation frequency at is for pure water is around at temperature 8.0 degrees centigrade is 8.9 gigahertz as measurement, and if it is 20 degrees centigrade, it's around 16.7 gigahertz. So that means for the calculations for the dielectric constant with respect to frequency, for example, the real part, also the imaginary part. So for the real part, it varies, or there is a quick change, maybe like this one. Two parts is F node, and for the imaginary part, it's really a maximum like here. So this is the F node, and so when it changes, the F node would also changes. That means the most of the maximum will also change. Here. Okay, and this is for the single relaxation, double the single relaxation, the Boy model. So single relaxation, the Boy dielectric model. So approximation of the another term represented is single relaxation, the Boy dielectric model. So at D2M to represent the abbreviation for this model, the name of it. So that means we just put our focus on the single relaxation term. So that means if there is a single relaxation, that means there should be also double relaxation. All right. So the next term is double the Boy dielectric model. So it can also the abbreviation of it is double the Boy dielectric model. So of course these three to represent that. So previously for the single Boy dielectric model, because as we said, it also depends on the measured data, and by fitting to the measured data, we get the values for all the parameters. So this model, it has an operation frequency range should be f smaller than 50 gigahertz, and according to the measurements, it can be correct when the operating frequency is smaller than 50 gigahertz. So if the frequency is larger than 50 gigahertz, this model there would be a great difference or separation or discrepancy between the measurement and the calculations. So for this part, the D3M comes, and it considers two double device. Double means the double relaxation frequency or double relaxation time. So its real part becomes as we previously noticed that the real part is infinity times 1 plus 2 pi j imaginary part f tw, right? Epsilon w node minus epsilon w infinity, like this one. And this is for the single divide. But for the double divide, because okay, this is the real part. So this is single divide. For the double divide, we would first separate it to be two terms. The real part first is your part plus 1 plus pi f tau w square, right? So epsilon naught minus epsilon w infinity, alright? But here, because we has two WY models, and we first took the first relaxation frequency. So this is to the first relaxation frequency and the first relaxation time, and plus the second relaxation time, W2 square, and this part is W naught minus is W infinity here. So this is for the this is single, okay? This is for the WY, and its imaginary part should be the same thing also. So it equals 1 plus pi f tau W1 square and 2 pi f tau W1 times W naught minus epsilon W1 times this term 1 plus 2 pi f tau W2 square and 2 pi f tau W2 times epsilon W naught minus epsilon W infinity. So this is the expressions for the real part and the imaginary part of the pure water based on the WY dielectric model. So this is for pure water. Okay. However, if we want to have, for example, the elliptic or the salt dissolved in the pure water, it becomes pure water with salt dissolved inside of it. We get salinity water. So for the salinity, we have S to represent that. All right. So as unit with unity as practical salinity unit. This is this unit, and it represents the the mass of the solid salt in grams with respect to the total mass of this material. So actually changes around from 0 to 40 per thousand. PSU, practical salinity unit. So for this part, so if there's salt dissolved inside of the pure water, the water gonna, or the material gonna, or the solution gonna has conductivity, alright? It will begin conductivity and divided by 2 pi epsilon naught times f, the frequency. So this is, if just a pure water, we're gonna have these two terms. This is for pure water. Pure water. If it is salinity water, so we need to consider the conductivity. Sigma I. So based on this equation, we can see that we have two relaxation frequencies. The first one we call it f naught 1 equals 1 over 2 pi tau W1. And then second relaxation frequency, it equals 1 over 2 pi for W2. So these two terms. And so as we previously said, the relaxation frequency for the single device is 1.8 gigahertz. This one is also at T equals 0 plus 73, all right, Kelvin. It equals 8.9 gigahertz, and the second relaxation frequency is around how much? It's around 201.8 gigahertz. A lot of difference between both, right? So this is 100, around 100. And for the double device dielectric model, it would not works. It cannot work at over the whole temperature range. For example, for water, if its temperature should always be larger than 0 degrees centigrade, all right? If it's below than that temperature, it becomes ice, all right? So its operating temperature range is 30 degrees centigrade and also times 273 Kelvin, all right? So transfer them to the Kelvin. And the operating frequency F here, it works at 0 smaller than 1 terahertz. So this is its operating range. So also, we can use these models to predict the dielectric properties of the pure water or salinity water over 1 terahertz range, but its frequency, its dispersion with respect to the environment would be very large. So this is for the salinity water, and so as we said here, the temperature should be larger than 0 or equal to 0, and so actually when we reduce the temperature of the water to be maybe from 30 degrees centigrade to 0 degrees centigrade, usually there would be no ice, all right? Because it transfers from the liquid water to 0 degrees centigrade. It cannot be 0. But actually for the ice, if we increase the temperature of ice from maybe minus 30 degrees centigrade to 0 degrees centigrade, and also the temperature or the ice would also be ice at 0 degrees centigrade and cannot be liquid water. So at 0 degrees centigrade, there is a mixture, and there is also the mixture of ice and water together, right? So when we want to calculate the dielectric constant of the water, maybe from minus 30 to plus 30 degrees centigrade, we would have different theoretical models to present that. And as our previous calculations or predictions, the calculations for the ice models and by the water models, there would be a sharp jump between both. There would usually a sharp jump between both at the temperature equals 0 degrees centigrade. So this is so for the calculations, we usually skip the calculations at 0 degrees centigrade. So now, what we're gonna consider first is for pure ice. So okay, let's do a short break, and then we'll come back later.
我们是那个反对的。微机电系统。啊？那个我第一晚上在读的。还没呢。
这个我们上个月没考。
没呢，我们这个礼拜今天晚上才开始读。会计。
没有。这个是啥？
还行，我们上个礼拜吧。很积极。把我们的小微包。
他这个月是不是发的上个月？
我们是人手。
啊，那并不像上个月吗？上个月是发的上个月。为什么？我以为你这个月发的上个月。我刚上个月初发了一个月，他们发的是发的上个月。啊！我靠，更不偏了，可能少100个，少一次这样。不是，我以为是先那个，就是发一个，就跟那个上班一样。我第一个不发，然后第二个发第一个，第三个就不知道。又说发这个月，完了，学会。我是。那么还有一个俩人上就不晓得俩关注。他来的，他你们？哦，这个，好像是。他们一考虑我以为前面
So for pure ice, so previously for the water, as relaxation frequency is at 1.8 or at 200 gigahertz around. So for the ice, its relaxation frequency F or F node is in the range of kilohertz range. So it's much smaller than that for the water. So that means in the microwave region, the 2 pi f times tau I frequency for ice. So it should be equals f or f node, right? So f is the microwave region, so f node is in kilohertz range. It will be much larger than 1. Alright. So that means the expressions for previously for the water, we can also use the same expressions, but it's going to be changed. So the for example, when we come back to here, this part is much larger than 1. Or this part is much larger than 1. Or this part is much larger than 1. That means all these terms can disappear, right? Can be neglected, and we can only get the real part. It equals real part infinity. And for the imaginary part, so here we also take the single divide. So it equals 1 plus 1 plus 2 pi I square by 2 pi f to I square I times epsilon I node minus epsilon I infinity. Alright? So it is, this part is much larger than 1, so it is equals to pi f to I squared pi f to I times node minus epsilon I infinity divided. So it equals epsilon I node minus epsilon I infinity divided by 2 pi f to I. And you can set, because these two terms can usually be a term used alpha node to represent that. So it equals alpha node divided by f. We get the expressions, and node also divided by 2 pi tau I. So this is the expressions for the ice, pure ice, the dielectric properties for pure ice. And actually, as we mentioned previously, for the single divide model, it is usually can only propagate, or it's only can offer the perfect or good predictions at lower frequency ranges. If we wanted to get let it to be more proper, suitable for the higher frequency ranges, we need to add another term for the correction, right? So, because as for the measurements, there is also because spectrum lines. There has another spectrum line lies in the infrared range, or infrared range. Region. So it added another term times f for the corrections, and so this is the expressions for the ice water for the ice and the dielectric properties for ice, and the alpha node, beta node is really for the some empirical expressions for them, and also the depends for different areas on the Earth. Their value is going to be different. So this is for the pure ice, and also what we're going to consider is the the kind of waters, the ice generally it cannot be pure, right? For water it may be pure, but for ice it's really difficult to be pure. For example, when the temperature decreases for salinity water, when the temperature decreases, because it has salinity or it has the salinity water gonna becomes the salt particles, right? Salt particles or pockets, and also there are some air pockets inside. So this would lead to the change of the expressions for the dielectric properties of the ice. So this is gonna be the next this we're gonna introduce later. So for if there are except or besides all these particles or pockets, there will also some impurity, especially for the ice on the earth. There will be maybe some soil particles, sand particles, or some other things inside of the ice. So it's gonna also modify or it's gonna change the actual measured or calculated values of the dielectric properties. So if there is the inclusions inside of the material, so for example, as we mentioned previously, we said we usually assume them to be ellipsoid, right? So let's assume there is a unit volume of material. Unit volume. And there are many kinds of ellipsoids inside Earth. Inside it. And so what we need to consider is we have several steps to take to conduct the theoretical model. The first thing is, because there are many kinds, there are just one kind of inclusions, and but the inclusions for each of them, if they are maybe close to each other, so there would be interactions between each of the inclusions inside of each. So the first thing is, for the assumption is, we neglect the interaction or the short range interaction. So that means the distance between two neighboring inclusions should be large enough, right? So that we can neglect interaction. So that means the concentration of the inclusions inside of the host material. So this is the unit volume is a host material. Inside host material is very low. So for a low concentration, we can neglect short range interaction. The first step. The second step. The second step is we assign an effective dielectric constant. We use the epsilon star to represent that. And this one is to account for the short range interaction. So this term to consider a short-range interaction. And the third part is, okay, we consider the influence interactions, but as according to the materials. Merely for the material analysis, their interactions, they have, for example, the interactions can be several orders of that, right? The first order, second order, third order, or much higher orders, and we just take the simplest, the first order interaction. And fourth, it is assumed that the size of inclusions much smaller than wavelength. So actually at microwave range, or maybe the lower frequencies, maybe most or almost most of the materials or the enclosures inside of the materials can satisfy static condition. So then we can take the further analysis on that. So first, let's come back to the one kind of a host material with only one kind of enclosures inside of it. So we have two kind of materials inside of it, all right? So in chemistry, we can call such a kind of material or mixture as a two-phase mixture. Two-phase mixture. So for the two-phase mixture, and the enclosures can be is regarded as the ellipsoid. So for an ellipsoid, for example, we have a kind of ellipsoid. Kind of ellipsoid, and its dimensions can be expressed by its three axes, all right? Along this axis, its length we call it 2a. Along this axis, 2b. And entering the plane of this axis, we call it 2c. So we have 2a, 2b, 2c to represent the axis or the dimensions of the ellipsoid. And so its volume can be how much? Its volume should be A times B times C and 4 pi L3, alright? For ellipsoid. It's correct. For sphere, its radius is r. Its volume is. Am I correct? So we have ABC. So this is for the volume of one ice particle, and if, as we said previously, is this host material is unit volume, all right? So it's dependent by one. And if each of the inclusions are identical to each other, so they have the same volume, and also their number is capital N in unit volume host material. So the VI is represented as the inclusion volume fraction. So this is VI. So divided by 1, we neglected. So it's 4A over 3 ABC times capital N. N is the number of the inclusions in a unit volume of the host material. So this is the volume of the fraction of the enclosures, and then the volume fraction of the host material becomes 1 minus VI. Am I correct? So this is the besides or except the enclosures, the loss of the volume is for the host material. So let's conduct or let's get the dielectric constant of the mixture. It equals, first is the dielectric constant of the host material times plus half of the volume fraction of ice or the inclusions, epsilon I minus epsilon H. Sum U equals the 3 axes and 1 over 1 plus AU times epsilon I over epsilon star minus 1. So this is an expression for the two-phase mixture. Two-phase mixture. Okay, and this formula is just a formula. So it's conducted by order 1 17 and the law. So by this guide, so it was called order 1 17 the law formula. So as we mentioned previously, epsilon star is the effective dielectric constant for the region surrounding an enclosure particle, right? So, and VI is the volume fraction of the enclosures, and the AU, the capital AU, is represented to capital AU. It represents a depolarization factor. A depolarization vector of the ellipsoid. The ellipsoid. So that means even though we assume all the enclosures to be ellipsoid, their dimensions can be a little bit different, all right? There should be a prolate ellipsoid and also the oblate ellipsoid, all right? So there are still also many kinds of shapes. So AU is used to represent that. So that means if the shape of the ellipsoid changes, the AU or maybe U can be AB and C, all right? So AB and C gonna change with respect to the shape of the ellipsoid. So we're gonna introduce that later. So it is usually can be so for the VI first. Vi is the volume fraction, alright? So when Vi reaches to 0, so there's no inclusions, so that means the dielectric properties of the whole material or the mixture equals the host material, alright? So when Vi reaches to maybe 1, the mixture tends to be the inclusions material, alright? It's filled, all the unit volume is filled by the inclusions, the material inclusions. So now let's come back to the depolarization factor. So for the depolarization factor, there is a general expression for it. It can be expressed as A times B times C, half of that, 0 to infinity, and integration times S plus U squared times square root S plus A squared times S plus B squared times S plus C squared. And this is integration for that one. And so we said, as we said previously, the depolarization factors depends on the shape of the ellipsoid. So that means for the ellipsoid, they should have a fixed value for the summation of all these 3 parameters, right? So it equals 1. So this is for all of the, no matter what the shape of the including changes, the total value of that, it equals 1. So now we would change the shape of the ellipsoids. For example, first as we call it plate sphere. Plate sphere. What is called plate sphere? So we find a picture. I have several pictures prepared for you. So this way. So this is the plate sphere, like that. Okay. So for the plate sphere, that means it's, so this is to C, alright? To C. And to A equals to B. So that means A equals B and smaller than C, alright? The length of it is larger than the S cross section. The length of S cross section. So that means the depolarization factor A equals depolarization factor B equals half of 1 minus depolarization of factor C. Alright, 1 minus AC divided by 2. And then AC is how much? AC equals to Q 1 minus A squared times ln 1 plus E divided by 1 minus E minus 2E. This one. And E, the small case E is the ellipsoid eccentricity. Ellipsoid eccentricity. And it can be, I think, in the mathematics there. They also use the small case E to represent that, alright? So it equals 1 minus A over C squared. A over C squared. So, and this is for the prolate sphere, and for the perfect sphere. So this one equals this one, okay? And for a perfect sphere, second. Perfect sphere. So, for such, as we mentioned previously, the sum of all these three polarization factors should equals to 1, all right? And A plus AB plus AC equals to 1. And also A equals B equals C, all right? Of course, the radius relate. So that means A equals AB equals AC equals 1/3. And this is for a perfect sphere. Also for the we squeeze it again, squeeze it further, then it becomes this one, right? It becomes like this. Becomes like this. This is oblate sphere. Or sphere. And we can say it looks like a rugby, right? Like a rugby. So now we can also have the A equals B, but now it becomes larger than C, right? Previously, if they are equal to each other but smaller than C, now it becomes larger than C. So, and also, then A equals AB equals half of 1 minus AC, but AC should be different than previously. 1 over A squared times 1 minus square root 1 minus A squared divided by E, and 1 over C E. So this is the expressions for the oblate sphere or the sphere, and also we squeeze it further, then it becomes the fourth one, becomes a disk. So it becomes a disk. So for a disk, that means we neglect so that means still A equals B, alright, and should be larger than C again, alright, because we squeeze it further, but it becomes much larger than C. So for it is much larger than C, that means now the dominant factor of it is only its length along this direction. So the depolarization factor of C should be how much? Squeezed too much that the dimension of C can be neglected, so the depolarization factor for C is how much? It can be neglected. It can be 1, right? Definitely depolarized, so it equals 1. So AC equals 1 means AE equals AB tends to 0. And then we have the back to this one. If we drag it, now this prolate sphere, and we drag it to much longer than that, so then it becomes the fifth part becomes needles, right? So we drag it much further, it becomes needles. So for needles, that means, as we assumed for according to this part, that means its dimensions at the A or A and B can be much smaller than C, right? So that means AA plus AB should be equals 1, and AC equals 0, and AA equals B, so that means A equals AB equals half. So this is for the depolarization factors for the different shapes of the spheres or ellipsoid. So based on these values, we can calculate, we can substitute them to this equation, and then we can calculate the dielectric properties of the mixtures with inclusions inside of it. So this is a general expression for that one, and we can just assume that if there is some inclusions inside of it, and we can get an equivalent dielectric constant of such a kind of mixture. Actually, if you take measurements on that, and there would be some discrepancies between the calculations and the measurements, because such an assumption is not enough for the theoretical models. So there is another model proposed. So this model has a special name. We call it TVB formulas. So T represent Tinga, and V as was, and also the B as velocity. So there are three guys, and they work together to conduct such a formula. And so in such a model, also there is the host material inside of it. Now we would just plot just one inclusion inside of it for an example. And for the calculations, we also set, because it's gonna interact with other inclusions, right? If we consider the short range interaction, but because we said it's a short range interaction, so its interaction area can be only also a small ellipsoid around the inclusion, and both are confocal to each other. So the most important of it is they consume, or they assume there is confocal ellipsoid for such a kind of material. So, and also they assume the dielectric properties for the inclusions epsilon I, right? Epsilon I, and the dielectric properties for the ellipsoid, or the shell, or the ellipsoidic shell, as it is the same dielectric constant as the host material. So now we assume that the length, the dimensions of the inclorant is to A, to B, to C, and we call it to A1, to B1, to C1. This is for the inclorant. And for the shell, it also has a dimension, right? Okay, so I will assume it to be 2 for the general expressions later. But for the shell, for the dashed lines, it is to A, to B, to A1, to B1, to C1. So this is for the host materials. So, and also there is, we accept they have a relationship as A1 square minus A2 square equals B1 square minus B2 square equals C1 square minus C2 square equals a constant P square. So the K square is just a constant, and it is determined by the volume fraction of the inclorants inside the host material. So now we know that for the inclorants, S volume is this one, right? For the shell, and also we consider it contains the inclorants inside of it. So its volume is B1, and C1 inside of it. So now if we want to come back to get this value, it equals V2 divided by V1, alright, like this one. And also the expressions for the dielectric constant of all these three mediums. All these three mediums is epsilon n, the mixture, it equals still the same thing, right? Epsilon h plus this I divided by 3, and epsilon I minus epsilon h, alright? The same thing as the previously what we said, this part, right? And what we're gonna change is just a volume part. So it becomes a little bit complicated, and yes, the same thing. Sigma equals A, B, and C, and also has to be 1 divided by 1 plus, here is epsilon I minus epsilon h minus 1, alright? The same thing as this part. Okay. But we substitute the effective dielectric constant as 3h, and here is another term. But now here it cannot be just AU. It should be, so this part related to AU2, this part related to AU1. 1 is representing A1, B1, and C1. U2 representing to A2, B2, and C2. So S A U2 minus A U1 times V I, the frame fraction, like the volume fraction. So this is the expressions for this part. And then when we come back to the parallel sphere, parallel sphere is a little bit more complicated. So just for the spheres, it's just 1/3. That means the inclusions. All these things should be A1, C1 equals A2, E2, and AC2 equals 1/3, right? And for the disk inclusions, it becomes A1 equals A2 equals AB1 equals AB2 equals 0, and also the AC1 equals AC2 equals 1. All right, and this here also the same thing. AB1 equals this one, and A2 equals AB2 equals 1/2 also, and AC2 equals 0, C1 equals 0. And also the same thing for all these parts. And all these things also is going to be changed based on this one. Okay, and HC2 also the same thing. And then we substitute them into this formula, the TVB formula, and we can conduct the calculations on this part. So this is the, as we mentioned, so this, no matter how the Van formula or the TVB formula, they are all under the assumption that this is a two-phase mixed, right? It has two kinds of materials. One is the host material with inclusions, one kind of inclusions inside of it, and also another thing need to consider is the volume fraction of the inclusions is much more than that of the host material. So that means that volume fraction cannot be very large. So, and this is for the host, the two-phase mixture, and also actually, for example, as we mentioned previously, for the snow, for example, it has air as the host, right, and it has ice particles, and also for sometimes it has a liquid water inside of it, so it becomes a three-phase material or mixture. So for such kind of mixtures, if we wanted to conduct that by these formulas, it can be very difficult, right? Because now, if we have another kind of inclusions inside of it, the expressions for these things should be changed or should be modified, definitely, and this increases the difficulties for the conductions. So we have another kind of dielectric mixing formulas, and this formula it do not have a unique name because its parameters usually cannot be predetermined. So it can be expressed as the simply expressed as H plus the volume fraction times I minus epsilon H. But here we have terms of and alpha is usually a constant. Just 1 minute. A constant. And so if it depends on the model that we gonna take, also the. So the model that we're gonna take depends on the properties of the mixture that we're gonna introduce next week. So for the linear alpha equals 1, for the refractive model alpha equals half, and for the cubic model alpha equals 1/3. So it depends on the properties of the mixtures. We're gonna introduce and continue this part next week. Okay? See you guys next week.还有一个是在那个，在那个你们办公室那会员，在应该在我们办公室看。然后直接和胡老师联系。就是你准备好了之后，然后到时候我进去跟他说。行，那我重新测一下那个。测一下哪个？行，那前两天冰箱电断了。冰箱电怎么断了？有点插冷关了，不知道哪儿有冰箱。把那个电源线关了。先测一下，看看有没有变化。行，还行。它应该不会变了，我觉得。它这是关了电源的话，对它影响应该不会很大。我感觉它好像吸收了点空气似的，带着变胀了，变窄了。变窄了？把氧气啥的吸收了，还是可以。把氧气吸收。行吧，那你再看看。或者你到时候测的时候，现场测会影响吗？为啥？如果不对的话，还要重新制备。为啥？万一不对的话，但是你可以还是不是还